which makes that radius a bit larger. So positive ions get smaller because they lose their valence electrons. And negative ions get larger because when they gain that extra charge, that nucleus holds on a little bit less tightly. And so these two graphs show the size difference. When we form positive ions, they get smaller. When we form negative ions, they get larger. Okay. Because each atom will gain or lose a different number of electrons, we don't have a nice trend for ionic size, right? And so I'm not going to ask you, to necessarily draw arrows on a blank periodic table saying which direction does the ionic radius increase. It's just a matter of knowing that if I take an ion and I make it, if I take an atom and I turn it into an ion, if it gains an electron, it's going to get bigger. If it loses an electron, it's going to get smaller. That's doubly true if it gains or loses more than one electron, right? If I have F to F minus versus O to O2 minus, O2 minus is going to be a really big ion, whereas Na to Na plus versus Mg to Mg2 plus, Mg2 plus is going to be a very tiny ion. And so the more we lose or gain, the bigger that size difference is going to be. All right, so in each of these pairs, we're going to see which of the two is larger. So negative ions, generally speaking, negative ions are larger or smaller than the atoms?
Larger.
That's it. And so if I'm gaining 1 versus gaining 3, which of those two species is going to be the larger species?
Nitrogen.
Yeah, this nitrogen 3 minus, absolutely. All right. So magnesium and calcium, both with a 2 plus charge, right? They're both in group 2. They both have lost 2 electrons. What do we think? Which one of these is larger?
Calcium.
Calcium.
And why is it calcium?
It still has more electrons, so it's going to be larger.
That's right. Yeah, the calcium lost its N equals 3 electrons. N equals 4 electrons, whereas magnesium lost his N equal 3 electrons. Yeah. And so calcium is the larger one there. All right. Fe2 plus versus Fe3 plus.
Fe2 plus.
Yeah, the fewer electrons we lose, the larger we are. Yep. Okay. All right, so good practice there. The last two trends that we're going to talk about, these last two physical properties that we're going to mention, both involve electrons. Ionization energy is the removal of an electron. Electron affinity is adding an electron. And so they have sort of different ways of thinking about the process. And so removing an electron from the gaseous atom in its ground state. So if we're removing something, let's say that's like sodium, now it tells us that it's got to be in the gas phase. And so we're going to Na plus, still in the gas phase, plus an electron, right? The energy, the change in energy for this system is equal to the first ionization energy of sodium, okay? i.e. ionization energy, okay? And I put a little 1 down there, and so IE1 we call the first ionization energy, and that's just removing the first electron. If we wanted to look at a second ionization energy, then I could look at something like this. Okay. And that energy would be the second ionization energy, IE2, right? And so, you know, if we have, sodium has 11 electrons, so it has 11 different ionization energy values, right? Between these two, ionization energy 1 and ionization energy 2, which do you think is lower in energy, a smaller energy difference? Pulling off 1 electron or pulling off that second electron? Okay, hearing none. Think about it this way. There's a positive 11 in the middle of that sodium atom, right? If he's holding 11 electrons, I'm going to draw a very crude diagram here. If he's holding 11 electrons, he's holding them all to some extent. But when I go to ionization energy 2, right, there's my 11 protons in the nucleus. Now I've only got 10 electrons that I'm starting with. So do you think that nucleus holds those 10 electrons a little bit stronger or a little bit less strong, a little bit looser than it does those 11 electrons?
Stronger.
Yeah, absolutely. So he's going to hold those 10 electrons a little bit stronger than he did those 11 because there's sort of a larger ratio of positive to negative charge, right? And so does that mean this change in energy is larger or smaller when I pull off that second electron?
Smaller.
If it holds if the nucleus and the electron has a stronger attraction, I actually have to put in more energy to pull off 1 electron. And so ionization energy 2 will always be a larger value than ionization energy 1. And so IE1 less than IE2 less than all the others, right? There's a second reason why for sodium in particular, the second ionization energy is very large, right? Sodium makes a +1 ion normally. Why does it only stop at a +1 and not go to a +2?
Because when it's +1, it's a noble gas configuration.
That's it. So if we have that noble gas configuration, that sodium at a +1, man, he's happy. He's got a full subshell. He's got a full N=2 shell. He does not want to lose any more electrons. And so it happens that the jump from the first ionization energy to the second ionization energy for sodium in particular is enormous, right? It's a very big gap between those two. There's a table in our textbook, and if we took a look at that table, we would see that for sodium in particular, the first ionization energy is about 500 kilojoules per mole. But the second ionization energy is about 5,000 kilojoules per mole. So it's 10 times higher, 10 times as much energy required to take off that second electron from sodium. Okay. All right. So here's that. This is a chart of just the first ionization energies. Okay. And you can see that the elements that have filled shells, helium, neon, argon, these are the highest ionization energies because their shells are full, right? Helium has the N=1 shell full, neon the N=2 shell, and so on. Those that are easiest to remove are the ones that only have to lose one electron to reach their noble gas configuration. And so they are, more than willing to give it up. That's why sodium reacts with water so violently. Water's happy to take that extra electron. He becomes hydroxide and hydrogen gas. And so sodium, when you put it in water, is a very violent reaction. And of course, all the rest of the alkaline metals do the same. If you care to, there are some fun YouTube videos out there of people putting both rubidium and cesium in water, and they are quite explosive. Before we leave this slide, I want to point out this little wiggle here in the ionization energy. And so lithium is 2s1, and then at this point, this is beryllium, he's at 2s2, and then we go back down to boron, he's 2s2, 2p1. And so beryllium at the 2s2, he's got a full subshell. Boron, 2s2, 2p1, has just one electron in that subshell. And so it's actually a little bit easier for boron to lose that electron because there's only one electron in there anyway. Once a subshell is full, it's harder to pull that electron out, right? That's why these are so high in energy, because all their subshells are full. But this little wiggle in between, right? We have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Why is there this little wiggle between 2p3 and 2p4? What do we know about the distribution of electrons in 2p3?
They're distributed.
They're equally distributed. They all have their own orbital, however you want to word it, right? They're all like this. That 2p4 comes in and puts an electron in one of those two orbitals. And so two things are going on here. One, we talked Monday about how having a half-filled subshell is more stable. And so first off, the 2p3 configuration is a more stable configuration than 2p4. The second is, remember that electrons are negatively charged. The whole reason Hund's rule exists is because two negative charges don't want to be next to each other if they don't have to. And so you have some electron-electron repulsion that is kind of pushing these two negatively charged electrons apart from one another once they're in the same orbital. And so that electron-electron repulsion actually makes it a little bit easier for that electron to be removed. It's not a whole lot, right? It's, I don't know, maybe that's 100 kilojoules per mole. It's not a whole lot, but it's enough to show up on a graph like this. All right, so that's ionization energy. That's removing an electron from an atom. So let's take a look at an example here. Which is going to have a smaller first ionization energy, oxygen or sulfur? Well, first off, neither one of these really want to lose an electron, right? They want to hold on to their electrons because they want to add more electrons to get to their noble gas rather than lose 6 electrons to get to noble gas that way. So the question really is, which of these two holds on to their electrons tighter, oxygen or sulfur?
Sulfur.
So maybe I worded the question funny. Oxygen holds on tighter, which means sulfur is going to have a lower first ionization energy, a smaller first ionization energy. So sulfur is the right answer for us. Right? So oxygen holds electrons more tightly. Who has a good explanation for that?
Is it because they're closer to the nucleus?
Absolutely. That's all it has to do with. All those oxygen valence electrons are in N equals 2. Those sulfur valence electrons are in N equals 3. Since they're a little bit closer for oxygen, he holds them closer to the nucleus. They're harder to remove. Sulfur, they're farther away from the nucleus, and so they're a little bit easier to let go of. How about between lithium and beryllium? Again, that first, we're looking at a higher second ionization energy. So higher and second ionization energy.
Beryllium?
Oh, if we remove 2 electrons from beryllium, the first one is valence or core?
Valence.
Valence. The second one from beryllium, valence or core?
Valence.
Yeah, that's right. So beryllium, the second electron is a valence electron. What's the second electron for lithium?
Core?
That's right. The second electron for lithium is a core electron. Is it easier to remove a valence electron or easier to remove a core electron?
Valence?
For sure. And so since the second electron coming out of beryllium is valence, he's going to have a lower energy. The second electron coming out of lithium is a core electron, so he's going to have a higher energy. So the answer to that B is lithium. Okay. All right. So ionization energy, removing electrons. Electron affinity is when we add electrons back, right? We talked about how metals tend to like to lose their electrons to get to that noble gas configuration. Non-metals like to add electrons to get to their noble gas configuration. And so when we look at electron affinity, we're talking about, let's do fluorine. Fluorine in the gas phase is going to add an electron to become F minus still in the gas phase. This delta E is known as the electron affinity. Now, it just so happens that for the vast majority of our elements, adding an electron is actually more stable because we have a negatively charged electron and a positively charged nucleus. Pulling those two charged things together is actually a little bit lower in energy. And so most of the time, let me change colors here. For most elements, this change in energy is negative. Right? That means that it's better. It's lower energy. It's more stable for it to be a negative ion, right? And so when we look here, it defines the electron affinity as the negative of the energy change. And so the electron affinity is always positive. Right? Okay. Now, unlike ionization energy, where we remove another electron, the second electron affinity doesn't really exist. The reason is if I have F minus in the gas phase and an electron, I have something that's negatively charged and another thing that's negatively charged. They're in the gas phase. If I try to make those two things collide, those two negative charges are going to repel each other. And so they don't really ever collide with enough energy for that electron to be added to the F minus ion. And so we do not get a reaction. And so there's no second electron affinity. Now wait, I hear you cry. Things have more than one negative charge. This is absolutely true. Oxygen, we know, is O2 minus, sulfur, S2 minus. The way that we get these multiple negative charges is by doing things not in the gas phase, right? We do things in solution phase, and that's where we get, that's how we're able to get these charges. Right? It's very rare for us to actually deal with most of these elements in the gas phase. That's just sort of how they define electron affinity and ionization energy so that it's the same for all elements. Okay. So a quick example, and then we'll slide into some groups and do the class kick. So the electron affinities of the alkaline earth metals are either negative or small positive values, right? So let me back up. I told you EA was always positive. Because the negative of the energy change, if delta E is positive, right, then our electron affinity is going to be negative. But that's a very rare case. But one of those reasons, one of those cases is these alkaline earth metals, right? So these have either slightly negative values or very small positive values. But in any case, these are very small electron affinities. Who's got a good guess as to why? What's full for all of our alkaline earth metals?
Their S subshell is already full, so it would have to be like creating a new or adding to a new subshell to add an electron. It's already pretty stable with the 2s full.
That's right, absolutely. So because they already have a full subshell, any additional electron would have to go into an empty subshell, and that's just going to increase the energy rather than decrease it, right? And so it turns out that this column has very small electron affinities. Can you guess another column here that's going to have also small or even negative electron affinities?
8,
Noble gas.
Yeah, the noble gases, right, for sure. These have negative electron affinities, right? Because what that means for us is they do not want electrons, right? So a large positive electron affinity, give me more electrons, right? Fluorine, his electron affinity is through the roof. He really wants another one. But right next door to him, neon, his electron affinity is very negative, right? Because he does not want another electron. All of his subshells are full. Okay. All right. So that's where I'm going to end this little mini lecture. If you'll give me just a minute, I'll get our breakup rooms set, and then I'll put you, you can get started on the class kick. Okay. The link for the class cake is on our Moodle page under labs. And so go there to get access to the class cake. Again, we just need one per group to be submitted. Okay.